Hello everyone. Have you ever waited in a line at a coffee shop and wondered if there is a secret formula predicting how many people will show up at the same time? Actually, there is. Today, we are diving into hypothesis testing for the mean of a Poisson distribution, a powerful statistical tool used to analyze random events happening over a fixed period. If statistics sounds scary, don't worry. I promise to make it as painless as waiting for your coffee order, or maybe even fun. Today, we will especially focus on how to test hypotheses when dealing with Poisson distributed data. Okay, let's get started. What is hypothesis testing? Before we jump into Poisson distributions, let's first understand hypothesis testing. Hypothesis testing is a method used in statistics to determine if a claim about a population is likely to be true based on sample data. We start with two opposing statements. Number one, null hypothesis at 0, the assumption that nothing had changed or there is no effect. Number two, alternative hypothesis HA, the claim that something had changed or there is an effect. Our goal is to use sample data to decide whether to reject at 0 or not. Simple, right? Now let's see how this applies to the Poisson distribution. Introduction to Poisson distribution. The Poisson distribution helps us model the number of times an event occurs in a fixed period or space. It is defined by a single parameter, lambda, which represents the mean number of occurrences. The probability mass function, PMF, of a Poisson distribution is given by the following formula. This distribution is commonly used in real-life scenarios like the number of customer arrivals in a shop per hour and the number of emails received per day or the number of calls at a call center per minute and etc. If you have ever wondered why every red light turns red light when you approach, that's Poisson's at work. Now let's discuss the properties of Poisson distribution. The mean and variance of a Poisson distributed variable are both equal to lambda. Events occur independently, meaning one occurrence does not affect the probability of another. The Poisson distribution approaches the normal distribution when lambda is larger, greater than 30. The distribution is skewed right when lambda is small, but becomes more symmetrical as lambda increases. Knowing these properties helps us decide the best approach for hypothesis testing. Formulating the hypothesis. Now, let's discuss how to formulate hypotheses for testing the mean of a Poisson distribution. To test whether the mean rate lambda had changed, we set up number 1, null hypothesis at 0. Lambda is equal to lambda 0. The mean rate remains the same. Number 2, alternative hypothesis HA. Lambda is not equal to lambda 0. The mean rate has changed. For a more specific test, we have number 1, left tail test HA. Lambda is less than lambda 0. The mean has decreased. Number 2, right tail test HA. Lambda is greater than lambda 0. The mean has increased. Picking the right test depends on what we are investigating. Test statistics for the Poisson mean. For hypothesis testing, we need a test statistics. For large sample sizes, typically n is greater than 30, the Poisson distribution approximates a normal distribution using the central limit theorem CLT. This gives us the test statistics as follows. This follows a standard normal distribution n 0, 1. For small samples n is less than 30, we rely on exact Poisson-based method, choosing the significance level and critical region. Once we have the test statistics, we compare it against critical values from the standard normal Z table. The significance level is typically set at 0.055%, meaning we have a 5% chance of rejecting a true null hypothesis. For a two-tailed test, we reject at 0 if z is greater than 1.96. For a left-tailed test, we reject at 0 if z is less than minus 1.645. For a right-tailed test, we reject at 0 if z is greater than 1.645. Let's go through an example. Imagine a call center records an average of 5 calls per minute. A new system is implemented, and after collecting data for 50 minutes, the recorded average is 4.2 calls per minute. We will test at 5% significance whether the mean number of calls has changed. Step 1. Hypothesis. At 0, lambda is equal to 5 versus at a, lambda is not equal to 5. Step 2. Compute the test statistics as follows. Step 3. Compare with critical values plus minus 1.96. Since minus 2.53 is less than minus 1.96, we reject at 0. In practical terms, this means that the new system has likely caused a significant drop in call volume, which might require further investigation. Additional considerations in Poisson hypothesis testing. Beyond just rejecting or failing to reject the null hypothesis, we should consider effect size. Is the observed difference meaningful in real life? Confidence intervals gives a range where lambda is likely to fall. Power of the test. How likely is the test to detect a true change in? Increasing the sample size can improve the power. Potential biases. Ensure the sample is randomly selected to avoid biases that could distort result. Practical applications of Poisson hypothesis testing. Hypothesis testing with the Poisson distribution is widely used in different fields like healthcare, testing whether the average number of patient arrivals in an emergency room had changed after introducing a new policy. Manufacturing, evaluating whether machine failures occur more frequently than expected. Traffic management, determining if accident rates at an intersection have increased after a road modification. Retail and businesses, assessing whether customer footfall has increased after a promotional event. These applications highlight how Poisson hypothesis testing helps in decision making across various industries. Expanding the impact, how Poisson hypothesis testing influence major decisions. Let's look at some areas where this kind of analysis truly shines. Supply chain management. In logistics, the number of deliveries or shipments arriving at a warehouse is modeled using Poisson distributions. Hypothesis testing helps supply chain managers evaluate whether an unexpected surge in deliveries is due to a significant change in demand or just random fluctuations. Manufacturing. In production lines, testing the number of defects in products over time can help identify if a new process or machine is causing more errors than expected. It could lead to necessary changes in production quality control. Insurance companies use Poisson distribution to model the number of claims that come in within a given time period. Marketing. Marketers analyze customer behaviors like the number of clicks on a digital ad or visits to a store using Poisson distributions. Hypothesis testing can reveal if a new marketing campaign has led to a statistically significant increase in customer engagement or sales. Hypothesis testing here can help adjust rates or assess whether a spike in claim is beyond what is expected. Public policy. Government agencies often use Poisson models to study incidents like accidents, crime, or disease outbreak. By applying hypothesis testing, they can determine if new policies are affecting the rates of such events. For example, after a city implements new traffic safety measures, they might use Poisson hypothesis testing to confirm if accident rates have decreased significantly. Conclusion. To summarize, when testing the mean of a Poisson distribution, number 1, define your hypothesis. Clearly state the null and alternative hypothesis before performing the test. Number 2, use the sample mean as an estimator. The sample mean serves as an unbiased estimate of lambda. Number 3, compute the test statistics using the Poisson normal approximation. For large samples, the normal approximation simplifies calculations. Number 4, compare the test statistics with critical values. This determines statistical significance. Number 5, draw a conclusion based on the results. If the test statistics falls in the rejection region, we conclude that lambda significantly differs from lambda 0. Number 6. Consider additional factors like effect size, confidence intervals, and power. Or statistically significant results should be interpreted in context with practical significance. Number 7. Consider the practical implications of your findings. If the mean changes significantly, it can impact real-world application such as optimizing workflows, adjusting expectation, or making business decisions. Hypothesis testing isn't just numbers. It helps in decision making for many real-world applications. Thank you for watching. Don't forget to like, share, and subscribe.